The way I actually became very passionate about this topic had to do with a personal experience where I tried to contribute more than a one-line patch to Postgres. It was related to SCRAM. And it ended up opening a new code execution path that led to a vulnerability disclosure that forced us to do an out-of-release cycle based upon the nature of the vulnerability. So I learned a few lessons in that. One, stick to the one-line C patches in Postgres, and I tried to contribute in other areas of the project. But two, it really made me want to dive deeper into how SCRAM worked, and really, what was the purpose of adopting this password method. And with that, I really started to explore and ask the question, what happens when you try to do password authentication in Postgres? It's such a common operation. So we're going to dive deeper into that today. We're going to look at some of the other password methods that have been available in Postgres, why they were used, what their weaknesses are, and then we're going to dive into SCRAM, look at that, and learn how to upgrade older systems to using SCRAM. So that all said, just a few things before we start. I'm with the Amazon RDS open source team. One of the great things about Amazon RDS is that it lets you focus on actually my previous world, being an application developer. Your schema design, your query construction, writing queries and making your application sing, while AWS focuses on everything else to keep your data up and running and available. We offer a variety of databases, Postgres, of course, my favorite, as well as MySQL, MariaDB, Oracle SQL Server, and there's Amazon Aurora with MySQL and Postgres compatibility. And again, the idea is to make it as simple as possible for you to manage your data, so that way you can focus on building out your applications and having them deployed. So as I said, the talk today, we're going to focus on password management in Postgres. And then we're going to look into how SCRAM works, because understanding how it works, it's actually a general purpose method that goes beyond Postgres. And you might actually want to consider including this algorithm at the application level when you're dealing with password-based authentication. So let's lock into Postgres. Very common operation. I was doing it this morning to actually prepare for the talk. Typically, you might use PSQL, you might use an IDE. But you put in a username, Postgres requests for a password, you might fat finger it, putting it in, and then you try again and ultimately you log in. But there's a question of what just happened? Like, what is actually going on when this happens? Like, is it secure? What data is being stored when I actually set up my passwords? And you start asking these questions, and it's really what is going on? So there's actually, before Postgres version 10, there were two ways for you to manage your passwords in Postgres. There was plain text and there was MD5. There was a method available called crypt, which integrated at the operating system level, but that was removed a long, long time ago. But the main two methods were plain text and MD5. So let's talk about plain text first, and then we'll go into MD5. And plain text was quite simply stored in plain text. If your password was password, then in the database it was stored as password. No big secret there. And this method was actually kept available for a long time. It was deprecated, I think, in the 8 series, but left so people could upgrade to the MD5 method, because the MD5 method actually has a special protocol that the connection drivers had to implement in order to use. What's interesting is you can actually still use plain text-based authentication in Postgres, but not in the way that you think. So if you're using LDAP as your authentication method, it's actually sending a plain text password over the wire and then over to your LDAP server. Postgres is basically just relaying it using the plain text authentication method. If you really want to use LDAP, you should look into the GSS methods or Kerberos, because typically LDAP is used to connect to Active Directory, and the GSS method will let you do that in a secure way. Oh, Kerberos. So those terms are interchangeable. KRB5 is one of the abbreviations in the Postgres docs for it, as well as GSS. So how does plain text password authentication work? Basically, as a user, I'm going to say, hey, I want to authenticate. Postgres is going to say, great, use the plain text method. Send me your password. If your password's data lake, it sends it over the wires data lake, and Postgres will either confirm or deny it. It's a simple equals within the database. And great, this works, kinda. The first major problem is eavesdropping. If you have someone next to it who overhears the conversation, basically that person has your password and can go through that whole authentication flow and can log in as you. So, we're not really well protected against that if we don't use any other methods. But we can use TLS. TLS protects us from eavesdropping. So we can encrypt, we basically can encrypt our communication so anyone trying to listen in can't necessarily hear what's going on. The slide details how you're able to configure this in Postgres, and these slides are written to be a reference you can look back at later as you need the notes. One cool thing I want to mention as a Postgres 12 is how you can actually force your client to present a certificate with another authentication method. So Postgres has something called certificate-based authentication. You would specify it using the cert parameter in the HBA-conf file. But in Postgres 12, you can actually specify something called client cert equals verify full. What that means is that you want your client to present you with a certificate where the common name is the client's username, and Postgres will verify if that is a trusted certificate within the certificate authority that it's using. What's cool is you can combine that with another method such as SCRAM and actually have a two-factor authentication system within Postgres. This is almost kind of a talk in itself. Working with certificates in Postgres is a talk in itself. I like to mention it because it's kind of cool that Postgres has a built-in 2FA mechanism. There's probably more work we need to do on that, but it's a start. Now, when you're using TLS, an imposter can't necessarily eavesdrop. It's walled off. But there might be a different way for the imposter to try to get the information. And here's a very common request. Hey, I'm in a development environment, there's a bug in production, can I just get a copy of all the data so I can inspect it and try running like my UI against it, make sure I can find the bug. So you can do a PG dump all. And when you do a PG dump all, and you look in the file, part of what you do with a PG dump all is you're logically recreating your database. So it's a series of SQL statements to reconstruct your data as you might see it in a different system, which means you need to recreate all the users. And when you look in and recreate all the users, what is that? There's a plain text password. And if this is your production data, you just gave your production passwords into like a development or a test environment, which means that someone who's has malintent, as they say, suddenly has your production credentials. So this is what led to MD5 authentication, because there was too many ways for users to be able, or I just say users with malintent, to obtain cryptographic. So MD5 authentication stores a password using the MD5 hashing algorithm. So there's some cryptographic security with it. And simply in order to set it up, you take your password, you use the username as a salt, and then you append the literal string MD5 to it. This, as I mentioned earlier, Postgres uses something called the MD5 protocol in order to do this authentication mechanism. It's very specific to Postgres. We'll look at an example of that on the next slide. But one thing I want to point out, an immediate weakness of this method is the salt. The salt is the username. So basically your MD5 password, if you use the same username and password on multiple database systems, which is common if you're in a larger environment, you might be using some sort of SSO technique, you actually have the same MD5 password in every single database. So if any of those databases get compromised and an attacker is able to learn that password, they can basically have access as that users to all the databases in your fleet. So that's one reason why we had to phase out this method. The workflow is actually fairly straightforward. If you're a user, you say, hey, I want to log in. Postgres says, cool. So we're going to use the MD5 method. I'm going to send you 4 random bytes. So the user has to do a 2-step process. And by the user, I mean your connection library or your client. You're probably not doing this manually. It's like, OK, well, I supplied this password to data lake. Here's my username. That's my salt. Make an MD5 hash and then append MD5 to it. Then I take the hash from that step, I append the 4 random bytes to it, I add the literal MD5 string, and I send it over to the server. The server, as you may recall, already has this stored. or at least it has the, that first MD5 hash here stored. So all the server has to do to verify it is basically take those 4 random bytes, append it to what it has stored, take the hash of it, add MD5, and if it matches this, then we know that's the user. This does protect against eavesdropping, because if the eavesdropper is going to hear that final string that comes through, and if they try to append those 4 random bytes to it, authentication is going to fail. So we stop that. But in through the outdoors, they say, PG dump all, I need to debug my information, and we have that original username password hash with MD5 encrypted to it. This is the credential. This is how you log in. And granted, if you're using PSQL or your IDE, yeah, this isn't going to work, but an attacker is not necessarily going to use that. They're going to have a script that's going to just put this into the correct form, speak the protocol, and use that to log in. So we're a little bit better, but we're not that much better because, as I mentioned too, there is actually a fairly wide surface area of attack, particularly if you're using the same credentials across your fleets of databases. And once the imposter has that credential, they can log in, very easily. But wait, there's more. There's other ways that you can compromise your credentials. Here's a typical way to create a password. I'm sure everyone has done this here. I mean, I certainly have. I did it today, in fact. I put in the plaintext password, in a SQL statement. This gets logged. And if someone has access to your server logs, they have your credential. The better method is if you're using PSQL, use the \password command. What this does is that this pre-hashes the password on the client side, so that way you're sending over the hash password to Postgres. However, it's still not perfect using this method because you're still logging the hash password to the server logs. And as I said with the MD5 method, that is your credential. It might not seem like it, but anyone can log in once they have that credential. Additionally, if you query the PG auth ID table, you basically have, if you're using the MD5 method, you have all the credentials in that regard. Now, it requires a privileged user, and I can say with confidence Amazon RDS prevents users from reading this table, but you need to keep in mind that if someone has those privileges, that you're trusting them not to impersonate anyone else in your fleet. These password methods need to scram. We need to get rid of them. We need to do something different. And as Postgres version 10, we did something different. We added the SCRAM method, the Salted Challenge Response Authentication Mechanism. What is really cool about this? The coolest part is not this big wall of text. The coolest part is all the RFCs being used. Postgres, being an open source database, likes to adopt open standards. In particular, the SQL language is a great example. That's where Postgres, changed its name in 1996 in order to say like, hey, we are implementing this standard language. And we try to stay as close to the core implementation as possible. I think we're at, it's like 160 out of the 179 SQL core standard blocks. And we keep adding more things to it, like the SQL JSON work, which I have a talk about that later today with Jim. SQL Med for dealing with remote data. But the idea was, let's use a standard method. It's well looked at, it's well supported. And the kicker is it's going to allow for 2 parties to verify they both know a secret without ever exchanging the secret. And that is a very powerful notion. Think about it. Let's say, I'm going to pick on Jim here since I've known him for a long time. Let's say I know the secret. Well, I know a secret and I want to prove that he knows a secret. But I don't actually want to exchange that secret directly. It's almost like I want to telepathically communicate it to him. This is kind of what SCRAM is doing. SCRAM is going to use a bunch of different cryptographic proof methods to be able to let 2 parties verify that each other knows the secret. It's almost like telepathy, but in the world of computers, because we don't have quantum teleportation yet, we do need to exchange some data. So there's 2 things we need to build up here. The first is we actually need to build up something called a SCRAM secrets, so that way Postgres can be able to do SCRAM authentication with the client. Then we can talk about the verification process. So first, let's see how we build up a SCRAM secret. There are 5 parts that we need. We need to know what our algorithm is, the number of iterations that we're going to go through, a cryptographic salt, and something called a stored key and a server key. So we're going to dive a bit deeper and see how all these things are built up. The first is the digest. which right now in Postgres it's just SCRAM SHA-256. This allows us to add additional SCRAM algorithms or potentially other password algorithms in the future. But for now, it's just the SCRAM SHA-256 algorithm. So other ones in the standard, I believe there's SCRAM SHA-384, 512, et cetera, et cetera. We introduced SCRAM SHA-256 Plus in Postgres 11 for channel binding, which we'll touch on in a little bit. And below, I'm showing what all the examples are if you want to try implementing this on your own later. Next is iterations. This is based on the password-based hashing algorithm we'll talk about in a few slides, and how many times that you're going to iterate over performing that method. Postgres by default uses 4,096 iterations. It's fairly high number, fairly standard in a variety of environments. But what's cool is if you're building your own SCRAM secret, you can set the number of iterations on your own. So I've tried it before. I set this to 8192. And it works. Postgres is able to adapt and be able to perform the password hashing correctly, or the client, I should say. Then we need to build a salt, and a salt is just a bunch of random bytes. Postgres by default uses 16. Again, you can choose your own value. I forget if there is a limit. I don't think there is, though. Thinking back to that vulnerability I was mentioning, I think that's where we discovered that there was a buffer overrun right in this part. That is now closed. So as long as you're on some newer versions of Postgres 10 and Postgres 11, you're not affected by that. Now it's going to get a little bit deeper. We need to build out the stored key and the server key, and this is where we start working with the original plaintext password. The first thing that we need to do is something called SASL prep. This is specified in the SCRAM RFC for how effectively it's normalizing the password before you begin hashing it. So it's in a standard fairly normal form. The thing with this is that the SCRAM RFC thinks about strings being encoded in UTF-8. Postgres can encode strings in way more than UTF-8. Anything from the SQL ASCII mode, which is kind of Postgres' way of saying encode in anything, I don't care, to a variety of different collations. And I'm going to show what the algorithm looks like on this slide. And again, this talk has been used as a reference for how to implement SCRAM, so I don't expect for everyone to read all of the slide right now. But the algorithm basically says this: if you have a UTF-8 password, go through SASL prep. If you do not, skip and just return the password. Now, and again, within Postgres, this is already handled, so you don't need to stress about it. But it's kind of cool to see how this works. All right, so we've now normalized our password. What we need to do is then generate the salted password first. So this is like the same thing as what we did. Well, it's similar to what we did with the MD5 password. This is ultimately your secret in a hashed form. And it uses the PBKDF2 algorithm, or effectively very similar to it. Again, the slides basically say how we get started with it and how we iterate over it. And this is really to follow along at home if you want to try to build your own SCRAM secret. As mentioned, it follows PBKDF2 pretty closely, and it's fairly simple to implement. Once you have generated the salted password, you then have to create the stored key and the server key. The stored key follows this method. And what is all this? So we're at this step here. The stored key is going to ultimately be on the server to verify this thing called the client key. So what's the client key? The client key is when you take an HMAC and use your salted hash password as the key to the HMAC and the literal string client key as the message, and you have the client key. What does that mean? So the client key, server key, and stored key are going to be an important part of what I call the SCRAM dance in terms of how a client and a server can verify that they know the secrets. We're basically cryptographically transforming the salted hash password into this thing called the client key using HMAC. And what an HMAC algorithm does is it lets you both verify the integrity of a message as well as the authenticity based upon the stored key. Based upon the salted hash password. Now, the client key is something the client is going to use during SCRAM authentication. And we need to put this into a form that the server can use as part of this verification, so that way we don't actually have to transmit the client key. Because the client key is also good enough to be a credential in SCRAM. So we take the SHA-256 hash of the client key and turn it into the stored key. And this puts it in a way where, unless you're doing some advanced man-in-the-middle techniques, you're not going to be able to decrypt like this part or decode that part. So then the server key. The server key is similar to the client key, where we use HMAC. We take the salted hash password as the key. We then take server key as the message, and then the literal string, and that gets output of the server key. Again, this is just to understand how we formulate all of this crypto. We'll walk through how this all works in the algorithm. The good news is that you don't need to worry about this when using SCRAM, unless you're trying to implement the algorithm. Now, so now we've actually built up the SCRAM secret, but Postgres has some shortcuts. \password will, if you're using PSQL and password encryption is set to SCRAM SHA-256, it will build it on its own. And what's cool is that, even if that is logged into your server logs, that's okay. We're going to see why that is. If your Postgres driver supports it, it can actually create the password and pre-hatch that password for you as well. Like, for instance, the CyclePG2 library does that. The drivers may delegate to libpq. That's the general C library that implements the Postgres protocol. Many of them do that because all of that logic is built in, and they don't have to go through all these steps that we went through. Now, what happens if someone eavesdrops on this? Like, do we actually care? And this is actually a very good question. The identifying information that we have about the credential in this is the stored key, which is hash of an HMAC using the computed salted password and client key, which is a mouthful, right? I think even that explanation, as I try to give it, you could see like, yeah, there's a lot I have to think about there. Like, this is something that folks who specialize in crypto look at. And same thing with the servo key. There's a lot of crypto there. That said, an attacker does have a few methods to be able, even if they have that SCRAM secret, there are some ways they can break the password. One of them is brute force. And if you're following generally good password methods, using a lot of entropy, trying to keep them longer, within the scope of the hash that you have, yeah, it's going to be very difficult to brute force for now. Compute is getting stronger. If they're very good, they can do an MITM attack during SCRAM authentication and derive the client key. That's the biggest risk there. The best practice is to use TLS when transmitting the SCRAM secret. You should generally be using TLS anyway to connect to your databases. I can have a very long debate on that after, but I generally try to push people in this direction for a lot of reasons. TLS, there is a little bit of overhead, but it's very marginal, and it's better to protect your information going over the wire than necessarily expose it and be vulnerable to things like this. Even better, if you are using TLS with Postgres, use SSL mode verify full, because that makes sure basically you're validating that you're connecting to the server that you want to be connecting to. If you use a lower mode like SSL mode equals require, all you're saying is that, okay, I'm over TLS, but I'm not verifying who I'm connecting to. Which, okay, well, at least your traffic is encrypted. You just don't know where your data is going. Yes?
Sorry, remind me what the store key is?
Sure. So the stored key is a SHA-256 hash of the client key. Cool.
And so the client doesn't use the server key, which makes sense. So this is the last, the store key is kind of the last bit of information that the client computes, and then sends that.
Correct, but we're going to see what the client does with the server key later on. This is just basically all we've done for now is that we've encrypted the secret, we've created the secret that Postgres stores that's going to be used in the actual SCRAM verification process. The fun begins now. So remember, our goal is we need to verify that two people know a secret without ever verifying the secret. Without ever exchanging the secret. We also need to make sure, and the key is making sure we don't exchange the sensitive information. And also we got to protect against other things too, like replay attacks. A replay attack is basically when you have, if the information doesn't change when you're exchanging, you can basically try as many times as possible to, crack a password or decode a password. And eventually the server might authenticate if you're not, refreshing information. And the best way to guard against replay attacks is to use nonces or like one-time strings or random bytes that have to change between session and session. And that's exactly what SCRAM does. So how does the authentication work? First you say, hey, I want to authenticate. Postgres goes back and says, cool, we're going to use SASL, which is a standard for exchanging authentication information, and specifically we're going to use SCRAM. So the user is going to say, great, we're going to SCRAM, and here's my nonce. This is the client nonce. Postgres is going to come back and say, okay, well, I'm going to generate my own nonce because we want to make sure each of us is in this unique session. I'm going to append it to your nonce. So we're going to have one super nonce. We have a hashing, we're going to be, we have this hashing method we need to use in order for you to, create, take your plaintext password and get it into the crypto that we need. So here's the number of iterations that we have, and here's the salt. Go for it. Prove that you know the password. So the first thing we got to do is we need to go through pbkdf2 again and take our plaintext password and convert it into that salted hash password. So this is what it looks like if you're trying to do this at home. So remember the client key. The client key is, we're going to take an HMAC. The salted hash password is our key. The literal string client key is our message, and we're going to generate that something called the client key. Remember that I said the client key is as good as being your credential for logging in. So technically, if we sent this over, if I took the client key and I took the SHA-256 hash of it, that's the stored key. And if we compare the two, then we would be good. But remember, that's what we're already doing in the MD5 algorithm in a different way. So we need to be better. We need to make sure that we're not just sending this over and giving, essentially, doing no better than we did before. We need to prove that we know what that stored key is to the server without actually sending this over in this form. And this is where we get something called the client signature. The client signature in the SCRAM RFC is defined as the HMAC using the stored key as your key, and something called an authentication message as the bits in it. And the authentication message is a bunch of the one-time information that's available when you establish the SCRAM session between the server and the client. It includes the nonce, includes some of the authentication headers. What we do is, I used to actually print all this out here, but it was, there's a lot of text. So, if you want to look up how it works, I would say, check one of the implementations or read the SCRAM RFC itself. So we have our client key, we have the stored key, and we create the client signature. We then are going to do one more thing and create something called a client proof, where we take the client key and we XOR it against the client signature. And this is how we're going to transmit that we know the client key / stored key without sending it over, because we take the client signature, which is a crypto mess, XOR it to the client key, and have the client proof. So we're not actually sending over the client key. We're sending over a jumble that if Postgres knows the password, it's going to be able to unpack it. It's going to be able to generate the client signature on its own, unpack the client key, and then take the SHA-256 hash of it and see if it matches the stored key. And this is how we're going to have the server verify we know the secret without ever exchanging the secret, in this case the password. We also have to keep extending the nonce over to the server, so that way we know we're in the same session. Now, how can the server actually do that? I'm making a very big claim right here. The thing is that the server can derive the client signature from the stored key in the session info, because remember, the server has the stored key already stored, and the server has all the session info because we've been exchanging it back and forth. So it can derive the client signature. And if we XOR the client proof with the client signature, we get the client key. Presuming that everything's done correctly, we have the actual client key, and if the SHA-256 digest matches the stored key, Cool, we've determined that the client knows the secret. We did it. The client is authenticated. We're good. Are we good though? Because all we've done so far is show that the server knows the client's password. Does the client know that the server knows its password? Like, how do we know that the server doesn't just say like, oh, you're authenticated, give me the data? So the client needs to prove that the server knows the password. And I will just make a side note. If you're looking at different SCRAM, different Postgres drivers that implement SCRAM, you want to make sure that they do this following step. I actually saw an example of one driver that did not, and I had to open up a ticket and say like, hey, no, like you can basically just have your clients now connecting to random Postgres servers that claim they know your password. That's not good because suddenly they might be start sending them data, and then who knows what's going on there. Fortunately, this step is not too difficult. So there's something called the server signature, which is the server key HMAC'd. The server key is the key with the HMAC algorithm. We take all the one-time information in the authentication message, and we use that to get the server signature. Because remember, I think I have. Remember, the server key, just replace the word client with server. I'll find where my diagram went. But as the client, if I have the correct salted hash password, I can derive the server key too. So the server's going to send the server signature over. And from there, I can generate the server key from the salted password, as I just mentioned. And then I can generate the server signature using the server key, based upon what we see over here. It's just server key, the one-time info, and we get the server signature. And the server signature that the server sends matches the server signature I generated. Then I know the server knows my password. It's not just claiming that like, oh, you're authenticated. It actually knows what's going on. And we did it. We never exchanged the password. That is really cool. This is why Postgres adopted SCRAM. Now, let's just recall one more time what was transmitted. The only identifying information was that client proof, which, as I mentioned, the client key is something that we can identify. Like, if you have the client key, you can log in as that person within that session. Or actually in other sessions if you're doing SCRAM correctly. But when XORed with the client signature, it's a little bit harder. Then you need to have the actual SCRAM secret to be able to decode the client proof, which is why I say you should protect that SCRAM secret when you transmit it. Then we have the server signature as well. And similar rules apply, but if you have, it's still that same cryptographic message. What else was sent? Nonces. They're only good for that session. Authorization headers about the session. They're only good for that session. So these are the two things you need to be concerned about with eavesdropping. They have the original SCRAM secret, and they're able to intercept the client proof in one-time headers. In which case, this one's a little bit harder because this is a timing-based attack. This one, they can do some offline work. So again, make sure you protect that. So what about a rogue server? Yeah. The one thing with SCRAM is you do need to consider this case. I mean, you need to consider rogue server cases in general, but in the context of SCRAM authentication, you need to consider this case. The first one we've already discussed, that Postgres actually says when it verifies the client proof, it says that you're authenticated. So that's why you need to make sure you verify the server actually knows the password. And again, this is general in SCRAM. TLS, you can say, well, wait a second, I'm using TLS. TLS verify full. I know which server I'm connecting to. Okay, but what if that server has been compromised in some way, and all you've done is that you verify that you connected to the server. You haven't verified that the server actually knows your secret. So that's why you have to do that additional step. Now, TLS, TLS itself, as we said, the main thing of TLS is verifying identity of a server and preventing eavesdropping, other people listening in. So how do we know that the server instance is the correct one? TLS verify full is actually a very good way of doing it, but Postgres 11 adds something called channel binding, which is another RFC that defines how do you know that when you've made a connection over the network that you're still connected to the same instance. Essentially, this uses information that's available in the TLS handshake. that gets passed into Postgres, from the handshake layer. And as a client, you can basically the Postgres client will specify if it wants to use channel binding or not. In my opinion, channel binding became very useful in Postgres 13, where the client can force channel binding. Up until then, there's the potential for a downgrade attack, where a client would just request for channel binding, and a Postgres server could say, well, no, I don't support channel binding. Let's just use regular SCRAM, which then leaves you potentially vulnerable to the first attack that we talked about, which is I can just claim that I know your password, and you start sending me your data. And again, my personal opinion, I think channel binding is great. You could use it with SSL mode verify full. In general, for your TLS handshakes, this should be good enough, but channel binding does add that extra layer of protection because you know that throughout your TLS handshake and your authentication that you are connected to the endpoint that you believe you should be connecting to. So how do you upgrade? Because hopefully, if you're not using SCRAM at this point, I've scared you all into wanting to upgrade to it as soon as possible. The good news is that Postgres 14 is acting as a bit of a forcing function of this because SCRAM is now the default authentication method. So first, ensure that your driver supports SCRAM. There's a wiki of a list of drivers that supports SCRAM. It's maintained lovingly by the community. And right now, there's only one on this list that does not support SCRAM. It was actually a driver I personally became aware of only, I think it was earlier this year or late last year. And now they actually, the driver author has a draft of SCRAM ready for it. The next thing you're going to do is in postgres.com, you're going to set password encryption to SCRAM SHA-256. Now, there's multiple ways you can do this. We're going to go through a demo in a second. You can use alter system. You can edit the file directly. If you're on Amazon RDS, I would say I recommend this blog that shows how to do it on this system. The one thing is, as you upgrade, you're going to keep MD5 as your authentication method in pghpa.conf. Why? Postgres was coded so that while you're upgrading all of your users from MD5 to SCRAM, both MD5 and SCRAM can work at the same time when you select this as your authentication method in pghpa.conf. What Postgres does is that it's going to check to see if a user has a SCRAM secret stored as their password. If it is, it's going to use the SCRAM method. If it isn't, it's going to use the MD5 method. So then the next thing is you have all of your users rehash their password using \password or pre-hashing the password locally, sending it to the server. And then once all the passwords are rehashed, you can safely switch pghpa.conf to use SCRAM SHA-256. Simple. Hopefully. Yes, sir. Hi, John. Correct. Well, I will show one method that could be used to force the change, but you're not going to like it. So yeah. And I just realized I can't demo it because I'm not on my computer. Oi. All right. So I effectively talked through the demo. Hold on. So there is one way you can force people to upgrade their passwords to SCRAM, and it's you basically set the pghpa.conf file to SCRAM SHA-256, and if they've not upgraded, they can't log in. Like I said, not a friendly method, but that is the forcing function. Now, there have been discussions of how can you help with the transition. Like for instance, if I know their MD5 password, can I put a layer in the middle where they log in with the plaintext password, it gets converted to the MD5 password, and then I take that and I convert that to a SCRAM password. You can do that, but then you have to maintain that middleware yourself. That's probably the easiest way to go, but it's really this is one of those things where you need to quote brute force it. You need to have all of your users in whatever way rehash their password. But this is actually probably a good discussion for the Postgres mailing list to see if there's anything we can do on the server side or even the libpq side to make this a little bit easier. Now, I had a really cool demo. I worked on it this morning, And unfortunately, I wasn't able to get my laptop to successfully connect. So if you want to see a live demo after this talk, I'm happy to do a one-on-one or one-to-many session on it with all my tiny little 13-inch monitor. So with that, let's conclude. The biggest takeaway for me from this, aside from avoiding making multi-line C patches that open up CVEs, is that not all password authentication methods are the same. It's something I think I've really taken for granted, coming from an application developer background. And yeah, I mean, certainly like when I was a teenager hacking on web apps, I would store passwords in plain text. Unfortunately, those were not like production apps. But then I would do simple things like, just have an MD5 hash of the hashword, then an MD5 hash of a hashword and a random salt. But then, thinking about just the flow of the information and like questioning like, why does this just work, does lead to better solutions. And in fact, even with SCRAM, you might, as I said, it's a general purpose method. You could use this for, let's say, web applications. And I was thinking about that, like, oh, you need a back and forth for that. That's typically not your web workflow. And sure enough, there is an RFC for doing SCRAM over HTTP, which lets you do SCRAM in a single call and response step, which is pretty cool. It's something that actually I want to dive deeper into personally. It's been on my list to read that RFC, but this is what's pretty cool is that, by constantly questioning, can we do better, we lead to better solutions. And as I've pointed out, even with SCRAM, like SCRAM is awesome. I think, SCRAM is certainly state of the art for Postgres for a while, but it's not perfect. We've pointed out a few weaknesses in the algorithm, to be aware of, and there's ways to work around them. But, you still need to be mindful of it. Hopefully we can get to a point with password authentication where nobody needs to know the secret in a way that you're able just to like exchange, non-identifying crypto, but then, multiple parties can verify that they know the secret, and even if someone has, the crypto used to do that, they're not able to do that. And and there's other, password authentication methods as well in Postgres that are certainly worth exploring, particularly if you're dealing with, larger fleets of databases. As I mentioned, Kerberos, GSS API. I'm a huge fan of certificate authentication, but with Postgres, certificate authentication does take work to be able to manage your PKI. As mentioned, Postgres 14 made SCRAM the default. You can still use MD5 passwords with Postgres 14, but you really, this is really us trying to say like, hey, like you should be, this has been available for 5 years now. You should upgrade to SCRAM. And even if you're on, Postgres 10 and and up, and you're not using SCRAM, you should make plans to upgrade it. There's enough weaknesses in the other methods that it will give you, a little bit more peace of mind in terms of those credentials getting out there. So thank you for attending. I'm happy to answer any questions.
For Postgres 14, making SCRAM the default, does it also set the default HBA to SCRAM as the default?
That's a good question.
Watch out for that if you're doing any of those upgrades all the time?
What's funny is I just generated it too. I think it's I believe it might still be set to MD5 just to help facilitate the upgrade, but I need to double check on that. It's also up to the package managers as well. So for instance, if you're installing from Debian, the Debian packages might have their own opinion for the default HBA file. Bruce or Jim, do you know off the top of your head?
When you say that SCRAM is the default Postgres 14, you really mean the default for storage and passwords on the server.
Correct.
Right?
Correct.
So we really didn't change
Yeah. I think.
the set, it's just the storage default.
Yeah. I'm trying to remember if we changed it in the HBA default as well. I don't think. Yeah. I was gonna say I don't. Yeah. It would be up to the package managers. Yeah. So it's up to the which in itself has been its own debate, but that I think it's up to for the package managers. Yeah. Yes.
If I need to move a user from, or not move, but just duplicate a user with the password intact from one non-replicated system to another replicated system, what technique do I use to never know the password and not make the user log into all 45 of my potential systems?
That's a good question. Likely in your case, you would need to have some sort of middleware in place to, effectively have them set it once and be able to move that password, in between. Now, you could do something similar where you pre-hash the SCRAM password and then send that credential to all the different systems. That makes it an easy user management problem. From a security standpoint, one of the benefits of SCRAM over MD5 is the fact that you have a variable salt. And with that variable salt, that means the SCRAM secret would look different on all 45 systems. So if you just make it once and send it to all 45, effectively, it's not as bad as if you have one, you have them all, because you still need to do some cracking once you have that SCRAM secret. But it's not you don't have the full benefit of being able to randomize all the crypto. But in the case when you're dealing with a large fleet and you need to upgrade and you don't want the user to log into all 45 systems, you either need to have a middleware where you either pre-hash the password or use some other crypto and then convert into random SCRAM across the board, or they have to log into all the different systems.
Okay. Cool.
Yeah,
Thank you.
you're welcome. Well, we have about 4.5 minutes. Any other questions? Great, well, thank you so much, and I hope you enjoyed the talk.